Hi everyone and welcome to this third video of BIOB20. In this video we are going to consider a problem from evolution. Let's consider the case that we have a species which has a protein in the ancestral form and that after a certain amount of time we produce the current version of the protein in the extant species. All we know is that within that period of time there is, on average, one mutation. It could be 0, it could be 1, it could be more. All we know is that on average there is one mutation. And now the question that I'm asking is, what is the probability that there is no mutation, 0 mutation? That's not an easy question to answer. For lack of a better idea, we are going to use the binomial distribution. We're going to split the time interval in two, and we're going to say that maybe there is a mutation in the first half, maybe there is a mutation in the second half, and the total number of mutations is the sum of whatever happened in the first half plus whatever happens in the second half. The way that we're going to model this distribution is to say that this is the binomial distribution with size of 2, each event having a probability of 1/2, so that the average remains 1. And we are interested in the probability that there is no mutation, x equals 0. The answer is 0.25, but is it the correct answer? You may argue not really, because here we have divided the time interval into 2, but we could have divided it into 4. So let's see if the answer stays the same in that case. The distribution would be size equals 4. We have 4 potential events, each of them with a probability of 1/4. Sure enough, the number is not exactly the same. So that depends on the number of subdivisions that we have put in the interval. Now, what is the right number of divisions that we must use? Well, we're going to see what happens when we try to make the divisions as small as possible. What's interesting is that when I make the subdivisions smaller and smaller, the probabilities change less and less. They seem to stabilize around a limit probability. At some point, when I have divided my interval into 1,000,000 and then into 1,000,000,000, I can see that the probabilities don't change anymore. They're practically stable. And that is the limit of the process, when the intervals can be considered to be infinitely small. The limit of that process is known as the Poisson distribution. We can check that when we use the function dPoiss for the probability of observing 0 mutation under the Poisson distribution, we get exactly the same number. This works not only for the probability of observing 0 mutation, but for literally any number we're interested in. For example, 1 mutation, 2 mutations, etc. This limit process that we've just demonstrated converges to the entire Poisson distribution. In conclusion, if we consider that the process is the sum of infinitesimal events happening over the whole duration, then there's exactly one distribution which corresponds to the given average of 1 mutation over the whole time period. And that distribution is the Poisson distribution. Now, what does the Poisson distribution look like? It would be really nice if we could make a histogram out of it so that we can see what are the numbers that are more or less probable in a Poisson distribution. So just like R binom and D binom, we have the function dPoiss for the probabilities, and the function rPoiss to generate random samples from the Poisson distribution. What we can do is that we can make the histogram of a random sample from the Poisson distribution. For this, of course, we use the function hist. Unfortunately, we see that there is an issue with the histogram. It's that it looks fairly ugly. For example, the numbers 0 and 1 are stuck together, while the other ones are separated by a space. It doesn't look very nice at all. We have a vague feeling for the distribution, but this is not a nice display. What would be much better is to take the output of d Poisson, which gives the exact probabilities, and make a histogram out of it, or at least a graph that would represent the probabilities as they are, according to d Poisson. We're going to use the function plot, and we're going to say x is equal to the sequence from 0 to 10, and y is going to be equal to the numbers of the Poisson distribution, to their probabilities, that is. We get this kind of plot, which is okay, but it looks a little bit dull. So we're going to work a little bit on the aesthetics in order to make it look more professional. The first thing is that we get these horrible label names. We will start with that. We are going to use the parameter xlab for the labels on the x-axis. We can say something like x, for instance, and for ylab, the label on the y-axis equals prob of x. We have much nicer labels this way, and it starts to look a little bit more professional. It can be difficult to read or align the values when you have a large plot like this. One nice thing that we can do to make it easier is to say panel.first equals grid. This will plot a grid, and then it will overlay the points from the graph. This way we can see a little bit better where things map on the x and on the y axis. Finally, the points don't really look like a histogram, and it would be better if we use something more like bars. It would look more like a histogram. One way we can do this is to say type equals h for histogram. We get bars instead of points. The vertical bars look more like a histogram, but one issue is that they're fairly thin. They're fairly small, especially in comparison with the grid. So we're going to increase the line width to 5 with LWD equals 5. And now they're really bold, and we can see a nice looking representation of the probabilities of the Poisson distribution. That is when lambda equals 1. This is not perfectly looking, but this is much better than what we had before. If we want to find another Poisson distribution, one with a different average, we just have to find a way to change the parameter lambda. We can set it to 2, for instance, to have 2 mutations over the whole time interval. And immediately we get a representation of what the distribution looks like when lambda, the average, is equal to 2. You can also see that the max and the average is around 2. This is what I wanted to show you about the Poisson distribution. Just like the binomial distribution, we have R Poisson to generate random Poisson numbers and D Poisson to know the exact probabilities of each event. In the second part of the video, I would like to show you how to manipulate data from other sources in R. The first function that we need to know is called read.delim. With this function, we can read data from many places, including your computer or the internet. We are going to take some data from the internet, which is something that I prepared for the BIOB20 class. One important thing about the function read.delim is that we need to assign the result to a variable. I'm going to call it prot for proteins. It's relatively short and easy to type. This works, but nothing happens because the result has been put into prot. The first thing I want to check is what the dimensions are of the data that I read in. The function is dim. I see that there are 22 rows and 3 columns. It's not very big, so I can print it on screen. It's not going to be overwhelming. You can see that the data nicely fits on the screen. We have the row numbers on the left, and we have 3 columns. They are called protein, time, and divergence. Protein is a string, time is a number, a numeric variable, and divergence is also a numeric variable. We have seen so far that some objects are called vectors in R, and one of the first questions we may ask is whether prot is a vector. The answer is no. The function isVector returns false. It is another type which is called a data frame. The function is.data.frame returns true. So prot is a data frame. What is the difference between a vector and a data frame? A data frame is a collection of vectors where each column is a vector of the same size. The way I can access a column is that I'm using the dollar symbol. Prot, dollar, and then the name like protein. Prot $protein prints all the values that are vertically in the data frame in the form of a vector. I can do the same for time. You can see that the entries are exactly the same. And of course, I can do the same with divergence. To demonstrate what I just said, is.vector prot $protein this time is true. Because protein is a column of a data frame, therefore it is a vector. The same goes for time and for divergence. A data frame is a collection of vectors of same length. Now, how do I access only the first element of the vector time? The way to do this is to use the square brackets. If I say prot $time square bracket 1, I get the first element, that's 0, the first element. If I want the second element, I replace 1 by a 2. I get 61.5, which is the second element. And if I want the third element, I of course put a 3 inside the square brackets. The square notation is very handy if I want to access only one element of the vector. But what if I want more than one element? If I want a range, for instance, I can use the syntax 1 colon 3. That will give me the entries from 1 to 3. When you do this, you get a vector of size 3 that contains the elements at position 1, 2, and 3. By the way, 1 colon 3 is the vector 1, 2, 3. I would get exactly the same result if I pass inside the square brackets the vector 1, 2, 3. You can see that the numbers are exactly the same. This is a way to have an arbitrary collection from the vector I want. I could put anything like 1, 3, 10, 22. The items are shown here, and they are taken from the vector at position 1, 3, 10, and 22. I can also change the order if I want. If, for instance, I put the first element in the last position, then the first element of the vector appears last in the output. The $sign is the way by which I access a particular column of a data frame, one column at a time. And with the square bracket notation, I can access a particular element of that vector, or a collection of elements from that vector. A data frame looks like a matrix. It's a square, so there is an index for the row, but also an index for the column. Another way in which I can get the same kind of output is to use the square bracket notation for both the rows and the column. For instance, we could say that we want the item in the first row and the second column, 1, 2. I can also take the item in the second row and the second column, or the item in the third row and the second column, and we get the same as before. This is an alternative way to access the elements directly from the indices of the rows and the columns. I can use the same tricks as before. I can have a whole range of rows, and likewise, I can also have a range of columns. And what I get is a mini data frame with 3 rows and 2 columns. This is a subset of the original data frame. The square bracket notation is very handy in the sense that you can pass any index that you like. It works for vectors, but also for data frames. That's it for today. This is what I wanted to tell you. Thanks for watching. Good luck with the quiz and see you at the tutorial.